Did you guys see the exam, practice exam I put up? I want everybody that wants to take it. Nobody has to take it. It's just practice. But I want everybody that wants to take it to take that today sometime. And then I'll close it this evening. And then I will reopen it again on Tuesday. All right. So you're going to have a chance to retake it. But I think it's going to be healthier if you take it initially. And I don't think it's going to be healthy if you just take it, screenshot every question, and then go back and study and take it a second time. We're not going to have points associated with this. And so the advantage is going to be to see what you need to learn, what you need to focus on. So trying to see where you're at. And then the second time you take the quiz, you'll have more time. You'll have the chance to kind of look over the quiz slowly, talk about it with your neighbors, with the book, internet, that sort of thing. Okay, so today is one chance to take it, and then later we can have multiple chances after that. It's not anything secret or anything like that. Just we need to really find out where we're at, and we want to do our best with the opportunity that this practice quiz gives us, practice exam gives us. Any questions about that? Okay. Other than that, we're going to start talking about Chapter 9 today. Okay. And 9 is a fun chapter because it talks about bonding in depth, right? We initially talked about kind of two kinds of compounds, and that has been our theme throughout most of this class, that there's two kinds of compounds. Aisha, do you know what those two kinds of compounds I'm referring to are?
Ionic and molecular.
That's right. We're talking about ionic compounds and molecular compounds, right? Compounds that are ionic are metals and nonmetals combined in some way. The strict definition of an ionic compound is it's made of ions, right? So, but that is, let me try to get this glare off. Okay, so that definition isn't very helpful. Made of ions, ionic compound, right? But we can usually recognize it if it has a metal, or, you know, a lot of ionic compounds contain the ammonium ion, NH4 chloride, for example, still an ionic compound, even though there are no metals in that compound, right? So, ionic compounds and molecular compounds. Now, molecular compounds are, the way that we identify them is they're made of nonmetals. But again, we have to be careful because this is an example of an ionic compound that has no metals in it, but it's made up of ions. So molecular compounds, carbon dioxide, water, that sort of things, right? No metals in it. And one more thing about molecular compounds in general is that molecular compounds consists of bonds in which there's electron sharing, as opposed to in ionic compounds, like we've talked about before. You have a metal, you have a nonmetal. They recognize that sodium will improve its conditions relative to well, we'll talk about it more in depth. Our stories before were sodium was sad because it had too many electrons. Chlorine was sad because it didn't have enough electrons. They decide to transfer an electron from sodium to chlorine, right? And then the resulting compound sticks together because of the charge, an ionic bond between them. Okay? And those are still kind of concepts and ideas that we can use, but we're going to talk more about this molecular bonding. So what's occurring when electrons are being shared here, all right? Because there are a lot of compounds. In fact, there's so many compounds that we have two other complete sections of chemistry called organic chemistry that deal with compounds that share electron density as opposed to an electron transfer reaction like the sodium chloride here. Okay, so here is the chemical reaction, right? This is chlorine gas in here.
A small piece of sodium metal is placed.
I can do the talking, so I'll put this on mute. Small piece of sodium metal is placed into a flask of chlorine gas. Okay, so we have some sand at the bottom of this reaction, right? Now the reaction doesn't initiate itself. It needs a little bit of heat, and in Chem 106 we'll talk about what's required to initiate a chemical reaction. For now, we'll just say that we're going to put in a drop of water. The drop of water reacts very vigorously with the sodium, and as soon as that produces a little bit of heat, then the rest of the reaction occurs where sodium is reacting with the green chlorine gas, and when it's done, you can see a haze, a white haze, and that's our sodium chloride, right? Our sodium chloride solid. All right, Alyssa, looking at that chemical reaction, would you say that that reaction is exothermic or endothermic? What did it look like, Alyssa?
Exothermic.
It did look exothermic to you? Why did it look exothermic? What were the clues?
Because like it looks like it gives off energy.
All right.
It's a solid.
Yeah. Gives off energy. There was a bright flash of light. I said that the sand was in there to prevent the flask from cracking because of the heat, right? So yeah, this is an exothermic reaction. Now, why is it an exothermic reaction? Where is that energy coming from? Well, if we look at the IE, what do you think IE stands for, Brielle? IE in this slide. What does IE stand for, Brielle? Maybe it'll help.
Is it from like the last unit?
Yes.
Ionization energy?
That's right, the ionization energy. So it's the energy associated with doing this, taking sodium and removing an electron. Okay? Now, Camilla, what did we say in terms of requiring or releasing energy when you remove a child from the family? What did we say? If you don't remember, just think about, what do you think? You would, if you have a family, parents, protons, children, electrons, and you remove a child or an electron from the family, what do you think that would do to the situation? Stabilize it or make it more crazy?
Stabilize.
No, nobody wants to lose a kid, right? It's not happy to lose a kid. Everybody would be crazy if you lost one of your siblings, don't you think?
Yeah.
So the process of taking an electron away from an atom requires energy, right? It's not a negative sign here. It requires energy. Okay? So this ionization energy is positive, requires energy. And let's see, that was Camilla. Is that true? Yeah, so Camille, what do you think in terms of energy? What did we say in terms of energy when we give an electron to an atom? What did we say about that, Camille?
Would it lose energy?
That process loses energy, and that's what our negative sign is here, right? Stabilizes the situation. Every family will take at least one spare child, right? Now the second one, no, that doesn't stabilize things. It makes it more complex. But again, the ionization energy, removing an electron requires energy. Taking an electron releases energy. All right? So the net energy change between those, and let's look at this, EA. What does EA stand for, Chance?
Electron affinity.
Electron affinity, that's right. And that's what we're talking about when we give an electron to an atom. So the net energy between the ionization energy of sodium and the electron affinity of chlorine is a positive value, 146.6. So the question is, well, why is this reaction exothermic if the net is 146.6? And the reason is because there's something else happening. There's something else happening in this process, and that's what we're going to talk about initially here. The other thing that's happening is what we call the release of lattice energy. Lattice energy. Okay? Now, here we have a picture of a material, an ionic compound in in positive and negative ions in a three-dimensional lattice, right? Three-dimensional lattice. And to take that three-dimensional lattice and move to the right here and split it up into its individual ions, pull them all apart, what do you think, Daisy? Do you think that would require energy or release energy to separate all of these ions from each other? Going left to right, Daisy, what do you think? Require or release energy?
My first guess would be it would require.
Yeah, that's right. It requires energy to pull all these ions away from each other like that. Okay? And thus, if I have all of these ions floating around and I can do the reverse reaction and form a three-dimensional lattice, Daisy again, that must what in terms of energy? Going the reverse process.
Energy?
It would release energy. That's right. And that's what happens in sodium and chlorine. You form sodium ions and chloride ions. They're not yet, right when you form them, they're not in a three-dimensional lattice. They're kind of floating around here, as you would kind of think about it, on the right side. But as soon as they begin to coalesce and form that the crystalline structure, a lot of energy is released. So here is down here, this third line, the energy associated with sodium ions and chloride ions forming sodium chloride. It's again, negative value, releasing 778 kilojoules of energy. So that makes the net process, here's our ionization energy for sodium, always requires energy to remove an electron, the first one. Always requires energy to remove electrons, no matter what, first, second, third, no matter what. Releases energy to give an electron to chlorine, right? But like we said, that's not a net negative yet. However, the resulting lattice energy that's gained when those ions come together to form a three-dimensional lattice is enough to make this process exothermic. Okay? Hopefully everybody can see that. Now, we have this diagram here, which will help us visualize this and talk about it a little bit more. Okay? In this diagram, here is where we start, where we have sodium solid, chlorine gas. We're only using a half a mole of chlorine gas because we're only interested in how much energy is associated with forming 1 mole, just for this diagram here, right? So we have a sodium atom, 1 atom of chlorine, represented by 1/2 of Cl2, right? And this represents their initial energy right here. This step here, which requires 107.8 kilojoules of energy, what does it look like we've done here in this step? Catherine, Ephraim, can you talk? Do you have the ability to talk, Ephraim? No microphone? So Catherine, what happens in this step? Can you tell by looking at these initial reactants and then looking at them here? What have we done? What's the change from the first to the second there?
I have no idea. I'm confused.
All right. Do you see how we have sodium solid and an atom of chlorine gas there?
And then sodium turns to a gas in the next state.
That's right. That's right. So we needed to form gaseous sodium atoms, and that requires energy, right? To take a solid to a gas requires energy. Very good. All right, Koa, you're next. If you look at this, the sodium gas and chlorine gas, now they're both in the gaseous phase. What's the next? What's the next thing we had to do here? Koa, can you tell by looking at this compared to this here?
Yeah, it requires energy to, I guess, form bonds. I'm not sure.
Yeah, we kind of break that bond, huh? Because it's Cl2 here, and now it's just chlorine atoms. Can you see that?
Right. Yeah.
All right, so for this reaction to occur, first we have to get sodium metal into the gaseous form, and then we have to get chlorine which is Cl2, into an individual atom, chlorine, chlorine, and that requires energy, always requires energy to break an atom. Where did the half go in the Cl2? Let's look at this really quick. So essentially, we started off with 1/2 Cl2, which is the same as 1 chlorine atom. And now it's going to just Cl atom by itself. So for an individual atom, it looks like we didn't do anything. But for moles of this material, you'd have lots of this Cl bonded to Cl, right? And now we're changing it to individual chlorine atoms because that needs to happen. We need to separate them up into chlorine atoms so that they can form sodium atoms. Okay, then let's look closer here now. We got sodium atoms and chlorine atoms ready to react. What is occurring from this point here to this point that requires so much energy? Whose turn is it? Kylie. What's happening there that requires so much energy? Looking at
It's being heated.
it's being what?
It's being heated up.
Well, no, we got sodium gaseous, chlorine atoms gaseous, and then now we have here what? What do we have? What's the difference?
Sodium has a positive charge.
That's right. We've ionized, and that's the energy associated with sodium ionizing. We've ionized the sodium atom. And that's consistent with what we've been saying. It requires energy to remove an electron from an atom. All right, very good. Let's see, does Leanta have a microphone there? No. Okay, Sarah, it looks like it's your turn. What is occurring here from this point? Sodium with an ion, or with a charge, chlorine, no charge. What's occurring at this step here, Sarah?
Chlorine is being ionized.
That's right. We're giving an electron to chlorine. That releases energy. Very good. And now we just have one more step. Are we okay? So we're back up to Aisha. What's the last step there that's occurring, Aisha?
Sodium chloride is formed.
That's right. And why is there so much energy that's released, Aisha?
Because it releases energy when compounds are formed.
Into a what? What do we call that?
Lattice structure.
That's right. Very good. So like we saw in this slide here, those ions now form a three-dimensional lattice and release a lot of energy. So these are the steps necessary. And you can think of these three positive steps as what we call an activation energy. A little bit of energy needs to go into the process before it can release that much energy. Overall, what we just saw in that flask was this going to this, right? And so the process released that much energy. We can't really visualize all of these steps that are occurring when we're looking at the reaction, but that is what's happening.
I have a question.
Yeah.
So, is the energy, the lattice energy, released spontaneously as soon as they start forming,
That's right.
or is it after the fact?
It's as soon as it begins to, anytime two atoms, or two ions, that are opposite charge come close to each other, they're going to stabilize themselves. The amount of vibration that's in those electrons are going to be stabilized because now they're getting electron density from each other. So
So in this reaction, the lattice energy was seen as the fire. Is that right?
Well, that's kind of hard to say. You're right. That, some might be in this stage while some are in this stage, but the energy being released is definitely can be released in the term. So when we see fire, right, when we see light or something like that, it is electrons stabilizing, right? Electrons being at some energy state and then going down. And when there's a transition, right, and this is one of the questions on the practice exam, when you have a transition from n equals 4 to, for example, n equals 2, right? From this sort of a transition, what do we expect to be released? Brielle, what do you expect to be released when there's a transition from 4 to 2?
Energy?
Energy. And what is the form of that energy?
I'm not sure.
It's a photon. It's generally a photon of what? What's a photon mean?
Light?
That's right, a photon of light. Energy. That's right. And the color of that light helps us know about kind of how much energy was released, right? Okay, so very good. Now, here's an important, very important question that I'm going to get you ready for, okay? There comes a point in your life when your children will ask you, Mommy, why is it that sodium takes the electron or gives the electron and chlorine takes it? Why doesn't sodium take the electron from chlorine, and why don't they form a compound where the sodium is the negative ion, and the chlorine is the positive ion, right? Wouldn't they still form sodium chloride? Have the same, similar lattice energy? Does everybody understand that question, right? Why can't sodium be the one to take the electrons? Why can't we just mix it up? What if sodium doesn't want to give up its electrons sometimes, right? Free will, right? So, well, the energy associated with taking sublimation, taking sodium to sodium gas, that would be the same. The energy necessary to break the chlorine bond, that would be the same. The energy to ionize sodium, instead of requiring 495.4, if we're going to instead use the electron affinity, so one is the ionization energy and one is the electron affinity, right? One is ionization and one is electron affinity. Which one of these is associated with giving an electron to the atom, Camilla? Which one of these is associated with giving the electron to the atom?
I really don't know. I'm like pretty confused.
Okay, so last chapter we introduced two terms, ionization energy and electron affinity, right? Ionization energy means the energy to do what? Do you remember that?
Ability to ionize.
Okay, that's right. That's right. The energy associated with forming an ion. And I don't know if you remember, but I said, I don't like the term ionization energy. Do you remember that, Camille? Or sorry, Camille. I said I didn't like the term ionization energy. I said it should be called what instead? Do you remember that, Camille?
I don't, I'm sorry.
Anybody remember that? I didn't like...
Isn't it like remember the cation?
That's right. That's right. Because ionization energy is kind of vague. It means the energy associated with forming an ion. Is that forming a positive or a negative? It's better to remember it as cationization energy, the energy associated with forming a cation. So this 495.4 is the energy associated with what? Giving an electron to the atom or removing an electron from the atom? Camilla, did that clear things up? What is this 495? Is that associated with giving the electron to an atom or removing it from the atom?
Are you asking me or Camilla?
Camilla.
I'm sorry, I still don't know.
Okay, all right. Let's make sure we back up enough here then to figure this out. So we have ionization energy. Did you catch, Camilla, what the ionization energy, I the better name for ionization energy? Did you catch?
Cationization.
That's right, cationization energy. So if we call it cationization energy, then basically what that is the energy associated with taking an atom and making it a cation. If I have to make it a cation, Camilla, what did I have to do? Did I remove an electron or did I add an electron?
Removed.
I removed an electron. That's right, that electron came off. So the ionization energy for sodium was the energy associated with removing that electron. Now, did that release or require energy? Chance. Did that release or require energy?
Require energy.
It requires energy. Now, is that just because we're dealing with sodium? Does it require energy to remove an electron from chlorine as well?
I would say yes.
And the answer is yes. Every element, it always requires energy to remove an electron. Okay? But if we give an electron to an element, right? Daisy, do you know how much energy is released when we give an electron to an atom of sodium? Do you know how much energy is released, Daisy, when we give an electron to an atom of sodium?
Would it be the electron affinity? So it would be -53?
That's right. 53 kilojoules of energy per mole is released when we give an atom or an electron to an atom of sodium. All right? Good. So that's what we have here. We have the energy associated with removing an electron and the energy associated with giving an electron. So remember the question. Could somebody remind us why what the question was? Let's see, whose turn is it? Joey, were you here for that? I don't know if you were here for that. What's the big question we're trying to answer here? We're getting ready for a question that our child's going to ask us in the future. What is it, Joey? Did you hear that one?
No, I did not. Sorry.
Okay. Catherine, did you get it? What was the big question we're going to answer when our kids ask us?
I don't remember it either. I just know it was big.
It was big.
Big question.
It is big. It's a big question. Our children are going to ask us someday, and we need to have an answer. Here's a hint down here on the bottom. Catherine, does that help?
Oh, if yes, I do remember. If sodium will ever gain more electrons and than losing one, right?
And
Something like
yes, at the expense of chlorine,
chlorine?
right? Yeah. So the question is, why does sodium always have to gain, or sorry, lose? Why can't sodium gain and chlorine give sometimes, right? Can't we just be friends? And so some people have to give and sometimes and not other people, right? So if we were to follow this bottom one here, instead of requiring 495.4 kilojoules, it would release 53 kilojoules of energy, right? And for chlorine, how much energy, Joey, can you tell by looking at this, how much energy what would the change of energy be if an atom of chlorine lost an electron? What would be the change in energy if an atom of chlorine lost an electron?
Is it the 348.8?
Okay. Is he right?
Wait, no, maybe not.
It's one of these two, right?
Yeah.
Which one of these has to deal with which one of these has to deal with losing an electron? Which one of these has to do with losing an electron? Is it electron affinity or is it ionization energy? Catherine, can you help him out?
No,
Oh, you got it, Joey? You got it?
well, if the number is negative, doesn't that mean that it's or giving and or releasing energy?
Yeah.
And so that would be gaining an electron.
Okay, very good. So it must be the ionization energy that's associated with losing that electron, right? So chlorine going to chlorine positive and releasing that electron. How much energy does that, what's the change in energy for this reaction, Catherine?
1,251.
That's right. 1,251 kilojoules for that process to occur. All right, so if we give the electron to sodium, it releases energy. But if we take an electron from chlorine, it requires energy. If we then add in the forming the bond, which is called, what is this energy called, Koa? The minus 787?
I'm not sure, actually. I wasn't there for the last class.
Okay. Well, this is just the stuff that we talked about today. Bringing those ions together.
Oh, no, you're right. It's the lattice energy.
The lattice energy. That's right, the lattice energy. So looking at all these numbers, positive 107.8, positive 121.3, negative 53, if we go this route, right, the electron affinity, giving an electron to sodium, positive 1251, taking that electron from chlorine, negative 787, that's the formation of the bond. We won't end up having a net negative change because this negative or positive 1251 is too large. So that's the answer. We say, I'm sorry, sweetie, but chlorine it will just take too much energy for chlorine to give up an electron. It takes energy for sodium to give it up, but not nearly as much as it does for chlorine. So you'll never see this occur. It will always be sodium losing the electron and chlorine gaining the electron. All right. I've just prepared you for the difficult conversation to have with your kids when it comes time. All right. This lattice energy, go back to this slide here. We have a list of these lattice energies. These lattice energies are always kind of given as positive values, but we have to know that it's the energy, if it's a positive value, it means the energy associated with breaking up the lattice. Whereas if you want to know how much energy will be released upon taking these ions and forming the lattice, these values would have a negative in front of them, right? And you can see that the things that govern this energy are the number of ions that there are, right? So we'll move ahead to this equation here. Their charge. So Q1 is the charge on one of the ion. Q2 is the charge on the second. And the size, because if the two ions can get very close to each other, then they'll be hard to pull apart. So the lattice energy is equal to, and you don't have to really memorize this, but it's just a general principle, right? The closer things can get, the stronger they'll stick together, and the stronger the charge that they have, the opposite charge that they have. So if we're looking at something like sodium combining with chlorine, there's some energy there. But if we look at something like calcium combining with carbonate, right? Top or bottom, which one will have a greater lattice energy? Whose turn is it? Kylie. Top or bottom, which one will have the greatest ladder energy?
I have no idea.
All right. The answer is the bottom. The bottom will have a stronger lattice energy. Any ideas why, Rebecca?
I actually just got here like 10 minutes ago.
Okay.
Confused, but
Sarah, any ideas? Why will the bottom one here have a stronger lattice energy?
Sorry, I'm not sure either.
All right, that's fine. Aisha, why will the bottom one have a stronger lattice energy?
I think you just said that the larger the charge,
That's exactly
the greater
right.
the
That's
energy.
exactly right. The larger that charge there, you're going to have a stronger attraction between each other. Very good. All right. So, we've already started this using electron configurations to determine ions. And these two slides here kind of talk about how that is done. And here are some examples, right? Sodium's electron configuration. We look at the highest the highest N value. We see how many electrons there are. There's 1, 3 s electron here. What do we call that electron, Alyssa, in this case? The electrons in the electron configuration that have the highest N value, what do we call that?
The valence electrons.
That's right. So there's how many valence electrons here, Alyssa?
1.
That's right. And so sodium is going to want to form a +1 charge to get rid of that valence electron. Very good. Calcium here, 2 valence electrons, and it's going to want to form a +2 charge. Okay, so we've done this, a lot of practice with this. Now, the octet rule is generally like one of the first things that people are taught in high school chemistry, and it's fine. It's helpful for a variety of things, but it's a little bit, I don't know, too simplistic, and it only kind of relates to our representative elements. It also relates to a degree to what we call our molecular compounds, and so we're going to kind of remind ourselves of that. What it essentially shows is that in this case here, for example, we have 6, 7, 8 electrons in our outer shell, right? The second shell, right? For calcium, forming a calcium ion, again, 3s2, 3p6, that's our 8 electrons in our outer shell. Okay? I think that we've talked about this enough. Yeah, we've talked about that enough. We don't need that anymore. So we've also talked about these. Here's one example that we'll want to bring up. Let's I guess start from the beginning. If we look at bismuth, right? Bismuth, whose electron configuration is as follows: 6s2, 4f14, 5d10, 6p3, element 83, right? So let me get out. Well,